Hello, this is Steve Spear, and this is Spear Talks. I'm going to talk about our second question on the 6.1 test. The second question, students did not do quite as well as they did on the first one. This first question, it's about a roller coaster. Derive an expression for the speed of the block at position P. Now, the way I would work this problem is okay, so here at the top, we're going to have potential energy, gravitational, and kinetic energy. We're deriving, so we should start with something off of our formula sheet, or some major idea. Now, we are not going to the bottom of the roller coaster, we're going to point P. So at the top, potential energy is going to be M times G times capital H. The kinetic energy is 0 because the velocity is 0. Now when we get to this point, point P, it says derive an expression for the speed at point P. So we're going to assume that the speed is not 0 when I get to point P. So at point P we will have gravitational potential energy and we will have kinetic energy. The gravitational potential energy is how high am I? So h over 2 is the radius. So if I draw a triangle right here, the hypotenuse is h over 2. And so this side right here is hypotenuse times sine, h over 2 times the sine of the angle. I'm going to add that to h over 2. So the height is going to be mg h over 2 plus h over 2 sine of the angle. And we're going to add to that the kinetic energy, which is 1/2 mv squared. We're going to solve this equation for v. So mgh minus 1/2 mgh minus 1/2 mgh sine theta equals 1/2 mv squared. Now I can put these two together and get 1/2 mgh minus 1/2 mgh sine theta equals 1/2 mv squared. I got a lot of 1/2s and a lot of m's. So I could factor out 1/2 m and divide by 1/2 m and they would cancel out. And I would have gh minus gh sine theta equals v squared. And taking the square root, I have gh minus gh sine theta. Now personally, I wrote this as the square root of gh, 1 minus sine theta. But that was not required. So on the rubric for question number 2, you were given points for correct application of conservation of energy, so that was this up at the top. 1 point for relating yp, the position at y, to h and in to theta. So this part right here was 1 point. And by having that in the equation down here, this stuff right in here, this part right here, gave me the second point, and the third point for correctly working the problem out. All right, and so 1 point for getting the math right. 3 points. Part B, to be honest, I was a little frustrated when I was grading this. Part B should have been an easy question, but you guys, several of you flubbed this up. In the question, in the prompt, it tells you that there is no friction. So do not draw any friction on this problem. Whenever we do frog body diagrams, I always ask you, what's the forces on point P? You said gravity. I said, what direction is it in? You said down. So draw the force of gravity, draw it down. I actually had someone draw the force of gravity perpendicular. And you have the surface pushing inward on point P. That's our normal force. So we have a normal force pushing in, and we have the force of gravity. That's it. Now, some of you drew a whole bunch of other stuff. You drew velocity as a force. No, don't do that. You drew a centrifugal force. Remember, we don't use the F word. Now, if you want to insist that there's a centrifugal force, it's fine, but it's point P pushing on the surface, not the surface pushing on point P. And these are the forces on P, not on the surface. So that's the answer. And you got 1 point deducted up to the maximum of 2 points for each extraneous force drawn. So some of you drew these two forces, got your 2 points, but then you lost 2 points because you drew a bunch of other stuff on there. Sorry about that. So that's the right answer. Part C says, derive an expression for the magnitude of the force exerted by the loop on the block. That's the normal force. When is it position P? Now, do not change your picture at position P, but at position P we had the force of gravity going down and we had the normal force going toward the center. Now, what we're going to do is draw our axis parallel and perpendicular to point P. I suppose I should say tangent and normal to point P, to the surface, to the curve. And force of gravity is not on that. However, you can break down the force of gravity into two components. This angle is the same as theta in that previous picture. Yes, theta. So this angle is theta. And so this little vector right here is the force of gravity times sine theta, which is mg sine theta. Newton's second law. Newton's second law is the forces added up equal mass times acceleration. But in this case, the forces are added up and they are centripetal. And they create a centripetal acceleration. There's a few people that were trying to confuse that. Remember, for something to accelerate toward the center, the net force has to be toward the center. And so the forces acting toward the center are the normal force and the component of gravity toward the center. However, we don't get to use AC in our answer. We only get to use the variables that were given. Now, on your formula chart, you have AC equals V squared over R. So, replace AC with V squared over R. Let me check something here. These are the letters we get to use. Notice that there's no R in that list. Unfortunately, I left an R in my answer and I got a point taken off. R should not be in my answer. So what would I replace R with? R is equal to H over 2. So F N equals M v squared, which, didn't we just find a formula for v? V was this number right here, GH 1 minus sine theta, and we're going to square that. So GH 1 minus sine theta. Okay, so there's v squared. We've got the mass. And now the radius was h divided by 2. And now I'm going to move this term to the other side, so minus mg sine theta. We're looking for Fn. Alright, so now we got to do some work here. When you divide by h over 2, it's like multiplying by 2 over h. That means the h's are going to cancel, and you're going to have 2mg minus 2mg sine theta, and then you still have this one, minus mg sine theta. And so minus 2 minus 1 mg sine theta means that the normal force is equal to 2mg minus 3 mg sine theta. Two minus 3. And so this was actually 5 points. So the 5 points were applying Newton's second law to more than one force. Some of you got Newton's second law, but all you put in here was Fn. You did not have the component of the weight in the direction toward the center. So there had to be more than one force there. For setting the sum of the forces equal to radial direction, in the radial direction, equal to mv squared over r. So some of you did ma, but you didn't do mv squared over r. You had to have that. For using the correct radial component of the weight is 1 point. For correctly substituting the speed from part A, recognizing that part A was part of part C, is another point. And finally, getting your work done right is another point. The next question threw many people for a loop. Calculate the angle L in degrees at which the block leaves the loop. The block leaves the loop when the normal force is equal to 0. When the normal force is no longer a force. When the size of the normal force is 0. So that means that this equation that you just came up with is equal to 0. So F2 mg minus 3 mg, was it sine theta, equals 0. Let me make sure I copied it right, because I've had a little trouble with that. 2mg minus 3mg sine theta equals 0 means that 2mg equals 3mg sine theta. So divide by 3mg. 0.6 repeating equals sine theta. Do the inverse of the sine, and you get that the angle is 41.8 degrees. The last question, we have a sphere now. And this sphere rolls down the track, rolls without slipping. So guess what happened to that potential energy at the top? It turns into potential energy at point P. It turns into kinetic energy translational and kinetic energy rotational. So not all of the energy ends up in translational. We have the same difference in potential, but since we have this rotational kinetic energy, we're not going to have as much translational kinetic energy. And so the velocity is less than. when it leaves. Okay, well thank you for watching my video, and I hope this helped.